Boa noite a todos, sejam muito bem-vindos ao canal Geotecnia Brasil. Para quem não me conhece, meu nome é Guilherme Campos Ribeiro, sou geotécnico e trabalho com consultoria na área de mineração. Gostaria de agradecer a você, colega de trabalho, que tirou um tempinho da sua corrida segunda-feira hoje para estar aqui prestigiando o canal e, é claro, principalmente ganhando conhecimento. Gostaria de agradecer também ao canal Geotecnia Brasil pelo convite de estar aqui hoje realizando a abertura da palestra. É uma grande honra estar aqui, especialmente neste momento em que recebemos um palestrante tão importante para a geotecnia moderna. Sem delongas, como todos nós sabemos, estamos recebendo hoje o renomado professor Jonathan Bray, com o tema Characterization of the Liquefaction Hazard. Agora, para dar seguimento ao evento, peço desculpa a todos, mas vou continuar em inglês para introduzir o tema e o nosso estimado palestrante. Liquefaction is a key factor behind many structural failures, especially in areas affected by earthquakes. Understanding liquefaction and its effects is very important for many engineering projects. That's why properly assessing the liquefaction hazard is essential to ensure the safety and stability of structures. In today's lecture, we will look at how liquefaction works and tools and methods to evaluate it and ways to reduce its impact. Our speaker today, Professor Jonathan Bray, is a well-known expert in this field. He holds the chair in Earthquake Engineering Excellence, and he is a professor at the University of California, Berkeley. Dr. Bay is a civil engineer and has served as a consultant on major engineering projects and peer-reviewed panels. He has authored over 450 publications on topics related to our presentation today. Dr. Bray is a member of the U.S. National Academy of Engineering and has received several prestigious awards, such as Bottom Seed Medal, Terzag Award, Ishihara Lecture, Peck Award, among others. That's a huge experience, isn't it? Please feel free to leave your questions in the chat and during the presentation, and at the end, we'll take some time to answer a few of them. Now, let's move ahead and give a warm welcome to Professor Jonathan Bray.
Thank you very much, and good evening, everybody. It really is an honor to speak with you today. And as he mentioned, I will focus on characterization of the liquefaction hazard. The outline for my talk is to review some key concepts in liquefaction, focusing on flow slide potential, and then highlight some of the field investigation tools that we have to investigate this hazard. And I'll use a project to illustrate some of the key concepts that I've laid out in this talk and end in a summary. So let's first talk about the liquefaction flow slide potential, which is really one of the most important things to assess early in a project. As you know, with a tailings dam such as this that can fail due to static liquefaction, a dramatic loss in strength with a brittle type of response, it can lead to damaging effects. And these types of slides have happened throughout the world, but this slide in 2019 really was the motivation for really moving things forward in terms of how we handle liquefaction and stability issues for tailings dams, very important structures. And these failures continue. So we have to be mindful of these concepts, overtopping failures such as that which occurred in September 2022 in South Africa. But just this year, we had a flow type failure in the Coupler heat leak pad failure. You can see videos online that actually show the slide in progress. This is one of the pictures of the slide. So these type of flow failures are still critically important and need to be addressed. And unfortunately, these failures come with fatalities. Now, if a dam or a tailings dam or any type of facility can fail statically, then obviously it's an issue in terms of earthquake performance. And one of the more important earthquakes in terms of the performance of tailings dams is the 2010 magnitude 8.8 Maller earthquake in Chile. And this slide shows some of the key tailings facilities that were affected by this large magnitude 8.8 earthquake. It's always important to recognize in performance-based earthquake engineering that there are many tailings dams that performed well. Some of these were upstream construction, some of these were centerline, some of these were downstream construction, but there were dams in the area that performed well. Unfortunately, there were tailings dams that performed poorly, and those are shown here in these red circles. All of these were upstream construction. And so we need to be even more mindful of this static liquefaction issue when it comes to upstream construction. And one of the dams that failed, the Las Palmas gold mine tailings dam, was closed. It had not been operating for about 2 decades, but it had been built and it's sitting there and the material's still saturated. This is what it looked like before the earthquake. This is a satellite picture showing the failure after the earthquake. And we sent a team from the Geotechnical Extreme Events Reconnaissance, the worldwide organization that does these post-earthquake reconnaissance and post-hazard reconnaissance. You can see some of the flow failure and clear evidence of liquefaction is ejecta. This led to the death of 4 people. And so whatever you're working on a civil engineering project, but especially an earth, water retention dam, or a tailings dam, one always has to look and say, are there materials that are in the dam itself or beneath it in the foundation that can lose significant strength as a result of cyclic loading or static loading if it's static liquefaction. Although I'm focusing on cyclic liquefaction for this talk. If you assign post-liquefaction residual strengths and do a classic static slope stability analysis and the factor of safety is close to or less than 1, then a flow slide is possible. Now, just because you pass that test doesn't mean you don't have an issue, because we could talk on another topic about if for those cases where we get significant deformation, you don't get a flow slide, but you get enough deformation. For example, the crest moves down sufficiently to allow an overtopping failure. So you do need to think about cases when you don't have a flow slide. And that key element there is estimating displacement, because that's an index of deformation. Many of the systems that we build, especially in the tailings industry, are built by hydraulic filling approaches. And it's important to recognize that these are layered systems. And so this is actually a picture of a tailings dam and a crack that formed, showing you the layering. And whenever you look at this type of system, you got to think about the fact that it's not the performance of this layer of material or the layer above it or the layer below. It's the system response. And it's going to clearly be anisotropic because of the way it's layering. For example, hydraulic conductivity is going to be much greater in the horizontal direction than in the vertical direction, and that affects drainage. And when you're instrumenting and understanding the instrumentation, you have to be mindful of the reality of the layered system. With liquefaction, it's important to also recognize that there is a hydraulic response as well as a mechanics response. So if this is actually a test performed at UC Davis by Idris and Boulanger and their team, where they built a slope, where they have sand and then they have silt layers. They shook this with an earthquake, and it did not fail during the earthquake loading. The slope failed after the shaking had stopped. It failed on a discrete surface, which you can see right here. And what happened from these sensors showed that water that was created, water that was generated because of the liquefaction phenomenon, moved up and hit this low permeability, low hydraulic conductivity barrier, the silt, and water accumulated on that layer. And that led to the void ratio actually being slightly higher there, and therefore the strength decreased, and then the flow slide occurred right beneath that interface. And so when you think about post-liquefaction residual strength, you can't necessarily take an element of soil, bring it in the lab and test it and get the whole story. You have to realize that most soils, such as this lower San Fernando Dam that had a large flow slide during the 1971 San Fernando earthquake, it's a layered system. And it's not just the mechanical response of the soil element to the seismic loading, it's also the movement of water. And as water moves up, it hits lower permeability layers, and you have water films and void redistribution occurring. And it's a system property. We talk about liquefaction. In fact, I talked about characterization of the liquefaction hazard. And I think that one of the issues you need to be mindful of is we say all these phenomenons are liquefaction, but we really should divide it into at least two subcategories. And I always like to look at liquefaction in terms of triggering. For example, that's where we start. We have a material that's susceptible to liquefaction. We want to know, given the seismic demand, as the cyclic stress ratio increases, the demand increases, and given the resistance, depending on the blow count, you can get a different resistance. You look at that factor of safety. And if the capacity or the resistance is, let's say, 20% greater than the demand, you have a factor of safety of 1.2. And so, for example, you may find a site in this location that has a low penetration resistance, but there's a low cyclic stress ratio demand. Factor of safety is 1.2. You may also find a soil in this case has a higher tip resistance, but the demand is greater, so the earthquake shaking was more intense, and yet its factor of safety is 1.2. A factor of safety of 1.2 is a bit misleading because you say I have the same margin of safety. That's why I always like to look at shear strains on the backdrop of this plot, because it's not just triggering, it's the effects of liquefaction. Here, if I'm a little bit off in my characterization, the resistance is a little bit lower or a little bit higher in terms of its penetration resistance, or the demand is slightly different. I go from maybe 2% shear strain potential to 3% shear strain potential, or 1% shear strain potential, maybe even 4% shear strain potential. It's a gentle hill. Where in this location, all the lines are coming together. It's essentially a cliff. If I have a little variation here, I might go from nothing happening and less than 0.5% shear strain potential to 20, 30% shear strain potential. And so think of it as at least two phenomenon. Flow liquefaction, and not that flow is necessarily going to happen, but it could happen. You're on a cliff, and I want to paint this red because this is the danger zone. This is where minor variations in the loading, minor variations in the properties of the material can lead to a flow failure with large strain potential. You can see the consequence here. It's loading, and nothing's happening in terms of shear strain until you get to a point where you get this brittle, large strain phenomenon. Whereas over here, you can get to liquefaction. If you take a denser soil and you load it highly, you can build up shear strain, and each cycle builds up a little more deformation. But it's a cyclic mobility with limited strain potential, as opposed to a flow liquefaction with unlimited strain potential. One of the more popular plots, and I know Professor Robertson spoke with you earlier this year in terms of one of these types of talks, and he showed this plot. So I want to bring this forward. This is looking at a shear stress ratio or large strain shear strength ratio, tau over sigma prime v. And we're plotting that versus the tip resistance. And notice that just like before, the number between flow liquefaction and cyclic mobility is conservatively about 80. On this same plot, the flow failures where we back calculate residual strains tend to be in areas where they have highly contractive soil response, where the tip resistance is less than 70 or so. In a zone between 70 and 80, you get partially contractive material. And then beyond about 80 or so, then you have dilative behavior. And so, again, this is kind of showing you that it's the looser soils with the low penetration resistance that should really be the focus of our attention. These are the contractive soils that can lead to large flow slides that then we can back estimate the flow failure strength from those case histories. We don't have case histories of flow failures occurring for highly dilative materials. The state parameter is a very useful parameter for looking at how far above the critical state line or the steady state line the soil is. And the higher it is, the more contractive it would be in undrained shear. Professor Ishihara actually defined an alternative way of looking at it, which is equally important, and that's the initial stress ratio. You look at the fact that if it's an undrained loading, it has to be, if it's a saturated material, it has to be at constant void ratio. And so it may be at this P naught, E naught. If there's something that perturbs it, it's going to shear and it's going to reach the steady state line at the same void ratio. And that ratio, P naught over P critical state, this physical distance in a horizontal axis, is actually very important in terms of brittleness. This is work that Professor Olson showed, that brittleness index, as defined by Bishop, which is shown here, so a brittleness index of 1 is a highly brittle material, that the more brittle the material is as that stress ratio gets higher and higher. And in fact, Professor Robertson, Peter Robertson, showed the same kind of thing on this kind of plot, where because these lines are curved, you get a better insight for undrained loading by looking at the initial stress ratio. Very high stress ratio here, 76. So there's a significant distance between where it's at and where it's going, and the brittleness index is very close to 1, a very dangerous situation, a very low residual strength. Here you still have an issue of a brittleness index of 45%, 0.45, and you have residual strength ratio 0.12. In this case, even though the state parameter is high, because of the curvature of the steady state line, the brittleness index is only 0.23. So look at it in terms of state parameter, but also look at it in terms of initial stress ratio. Another important thing is the critical state line or the steady state line are independent of the initial state or the fabric of the soil. They're the large strain state that the soil will eventually get to. And so the steady state concept is incredibly valuable as a framework, but it's insufficient to handle all the details that matter to us in seismic engineering, as well as static liquefaction. We have to also think of what Professor Ishihara termed the quasi-steady state line. There's a line that if you go to, you don't just go to this line on a horizontal plot, you go actually past it, come to the quasi-steady state line, and then head back to it. So you eventually get to the steady state line or the critical state line, but you go somewhere before you get there, and that's called the quasi-steady state line. You can see that on this plot here that I have here, going to the quasi-steady state line before you get to the steady state line. The important thing to remember is the quasi-steady state line does depend on fabric. It does depend on the depositional history. You can have two soils with exactly the same relative density, exactly the same void ratio, but they have different fabric, and therefore they'll have different quasi-steady state lines. And the quasi-steady state strength is really the strength that matters most in the field, because in the laboratory, you can keep the specimen together and get to the steady state line of R. But in the field, the soil will start to fail and break apart. And so the key thing here is the quasi-steady state. And this tends to be at a state parameter of negative 0.05, not at 0. So the quasi-steady state line is critically important. And I'm just bringing this data from Ishihara for a sandy silt material. The sandy silt, it's the same material. It has one unique steady state line, pointed out here by this red arrow. This is the steady state line. But if it's formed in dry deposition, it has this line as the quasi-steady state line. The same soil is built by water sedimentation. This is the quasi-steady state line. And so a soil here, if it's dry deposition, will go to the quasi-steady state line and move shortly over to the steady state line. The same soil here will go all the way over to this location, the quasi-steady state line, before it gets to the steady state line. And the quasi-steady state line depends on fabric. So you care about soil fabric. Fines content is often used in characterizing a soil. And for well-graded materials, I think fines content is a good proxy for compressibility. But for uniform soils, such as these soils, which one's a silt, one's a silty sand, and one's a sand. But if you look at the photographs, they are the same minerals, the same particle shapes. These are just a little bit smaller. And you want to ask themselves, does soil know that this 200 sieve, which divides coarse grained materials from fine grained materials, does it exist or not? It doesn't matter if there's uniform soil. If I have a uniform soil, the difference between a very, very fine sand and a very, very coarse silt is just a minor translation. Nothing fundamental happens as you cross the 200 sieve. And so be mindful that some of our proxies, like fines content, are not as good as other parameters, such as Robertson's soil behavior type index, I sub C. In fact, this is driving that point home. These are laboratory tests on those three soils I just talked about: the clean sand, the silty sand, and the non-plastic, low plasticity silt. In terms of stress strain, let's not look at effective stress plots. Let's just look at shear stress or normalized shear stress versus shear strain. That's the engineering response of the material. They all essentially look the same. And so there's not a difference between the clean sand response and the silt response when it comes to this material. The other thing that there's been much debate about is what soils are susceptible to liquefaction. And again, what's most important is the engineering consequences of the material. So we're looking at a deviator stress normalized by the initial effective stress that the soil was consolidated to versus axial strain. So these are cyclic triaxial tests. We have a clean sand in black, a silt that's non-plastic, and two silts that have plasticity indices of 10. There's no significant difference in terms of their stress strain response. And therefore, we shouldn't call them different things. If we're going to call the clean sand cyclic liquefaction, then we should call the silt cyclic liquefaction. And the Bray and Stansfield criteria, where PI is less than or equal to 12, is based on that consequence. There's other definitions out there, and they're good definitions, but go back and realize, what did they base their definition on? If it's based on how you're going to attack the problem, then that's a different definition. So some of the conflicts that people have seen between different liquefaction susceptibility criteria are because of the different definitions of liquefaction. I like to call our procedure a cyclic performance assessment criteria. What everyone agrees on that I've interacted with from all different viewpoints with different definitions is test the soil. Because the reason why the late Professor Harry Seed moved into doing penetration resistance is because it was difficult to get an undisturbed sample of clean sand. But you can actually get good, high-quality specimens of high fine content soils. You can sample them effectively. So let's look at the field investigation tools that are available to us. I just list some of the key things here, and obviously we always start with geology. So much can be learned by talking to an engineering geologist who understands how the foundation materials have been deposited by nature And then you think about how the materials that you have, let's say within and retaining, being retained by your tailings dam, or being formed. Geophysics are incredibly valuable. And then the geotechnical tools, I've listed some of the key ones here. Our primary tool is typically the CPTU or the seismic CPTU, but we shouldn't forget about the field vein test, especially for foundation materials. They have higher clay content, soil sampling, so we can do high quality testing, other penetration resistances, and I'll talk about the importance of detailed logging. So don't forget geology. There was tremendous ejecta and liquefaction in the eastern suburbs of Christchurch, New Zealand, as a result of the earthquake sequence. Once we got our handle or our mind around that, we started looking at southwestern part of Christchurch and realized there was supposed to be significant liquefaction there too, according to our methods. We did have some zones that had ejecta, but we had a lot of areas where our CPT-based methods and our SPT-based methods said there should be no liquefaction. Should be liquefaction, but there was no liquefaction. So the methods were saying you should expect liquefaction, but we saw no liquefaction. When we sampled those, we saw that these were not the classic thick, clean sand deposits or relatively homogeneous materials. They were highly layered materials, overbank deposits, and that kind of depositional environment made it less likely for ejecta to form. As I mentioned, our primary tool is the CPT, and one of the indices that we use quite often is I sub C, but take a look, if you haven't already, at the Robertson 2016 updated soil behavior type index, which he calls I sub B. They're both valuable to look at, but the most important thing in many respects is it a sand or is it a clay? And more importantly, is it dilative in drain shear or is it contractive in drain shear? Because if it's contractive in drain shear, then when it's undrained loading, that contractive response is going to lead to high excess pore pressures, which are going to cause the effective stress to go down, which is going to cause the stiffness and strength to reduce dramatically. I also like this in the sense that he's added a transition, because there's not sand behavior and clay behavior. There's always sand-like behavior, clay-like behavior, but then there's always a transitional material. Some silts act more like sand, some silts act more like clay. And so I like the fact that he's got this transitional material in there. As I mentioned, the field vein is a very useful tool because in many respects, what you care most about is what is the peak strength and what is the residual strength. And this test, by putting a vein down and spinning it, you get a direct measure of the peak strength and the residual strength. It's especially useful for clayey type materials. I work around the world and I am disappointed when I get SPT, standard penetration tests. And there are ASTM standards that tell you how to do this test. But I often get data like this, where they just, without describing what they did, I just get blow counts of 5, 25, 27, 37. I have no idea whether those are right. I've measured blow counts that were half of what people told me they were, and I've measured them that they were double, because so much depends on the energy. And so my recommendation to you is, if you're going to use the SPT N value to do a liquefaction assessment or to characterize the soil, you must measure the energy. It's not difficult to have 2 accelerometers. You only need 1, but you have 2 for redundancy, and some strain gauges because the rod's elastic, and you can then integrate the strain and get the displacement, or I mean the force, because you get the strain gives you, with the elasticity, Young's modulus of the steel, and the area of the rod gives you the force. And then by actually integrating the acceleration time history, you get velocity. With velocity and force, you now have the energy blow by blow. And one of the devices I use is the SPT analyzer, but there are a number of other pieces of equipment out there. But the key is you measure what the energy is. Go out there and attach this to equipment where the operator goes, the energy is 82.3%. And I go, well, I'm not going to trust you. I'm going to measure it. And I've measured energy on systems as low as 30% and as high as 110%. There was a system that was actually pushing on the rod to lift the weight up. So it was actually more than 100% free fall energy. And so since the blow count is directly related to the energy, I measured energy. I've measured blow counts that are double to half of what other people have measured when I've actually put in the correct energy. So if you're not going to use the blow counts, don't measure energy. But if you're going to use the blow counts, measure the energy. And then I wanted to mention this, that with the CPTU, there's a tendency, because you can go fast, to get your tip resistance, to get it as deep as possible. Stop and do dissipation tests, because that gives you important information about where's the depth of the phreatic surface. Maybe you have a perched water table, maybe you have several different layers, maybe you don't have hydrostatic conditions. It also gives you a chance to get the estimate of the hydraulic conductivity, at least in the radial direction, as you do that test. Sampling can give you an idea of where you have oxidation and where the groundwater might be. And sometimes the groundwater actually level is up here, and what you care about is the soil that's saturated or nearly saturated, because that's the soil that's going to liquefy. So water is obviously a key element, and getting good, high quality data of where the phreatic surface is and where the depth to saturation is. If you're going to do soil sampling, do high quality soil sampling. Otherwise, take poor samples and do index tests. That's fine for that, sieve analysis, Atterberg limits. But if you're going to do a cyclic triaxial test or a cyclic simple shear test and use that to calibrate your model, you absolutely need high quality soil sampling. I'm a big believer that it has to be a Osterberg type fixed piston. You cannot take a Shelby tube and push it into the soil, or take a thick dimension sampler and get high quality samples. And so, of the samplers that are out there for routine use, my favorite is the Dames and Moore hydraulic fixed piston sampler. It's an Osterberg type sampler. It's thin walled, constant inside diameter. All these details matter. And I actually have a document I can share with you that has the details on how this operates and how you should do drilling and sampling with this device. Once you have the soil in the tube, that's the first thing you need to do, right? But then you need to continue with that. And you need to treat these like your children. Put them in a car seat, keep them in the same direction, and then take them to a lab that's close to your site. Shipping them halfway across the world to a better lab is not necessarily the right thing to do, because you want high quality specimens. And through the transportation process, they can become disturbed. And then when you get them in the lab, the least amount of soil, at least amount of tube that you can push the soil through, the better. So I actually will put stiffening rods so I don't get the tube to buckle, and I'll cut it very carefully, and I'll extrude the least amount of soil through the sampling tube, and I will make sure that I do it in a nice steady manner. I'll place the sample and then I'll test it. This is showing you some effects of disturbance. This is relatively reasonable. You can see the laminations are showing you that it's fairly good, but as you push it more into the tube, it gets more disturbed. This one was overdriven and showing you how bad things can get. This is a case where the thing was hammered in place. So hammering any kind of device that is not smooth, the faster the tube can shoot, and the smoother its action is, the more high quality the specimen. high quality, poor quality. Soil response depends on, yes, density and stress, but it depends on fabric as well as other issues that need to be preserved. So if you're going to make sure that you capture important effects like fabric, microcementation, aging effects, you have to have high quality undisturbed specimen. And this is showing you a liquefaction resistance curve for a soil that's been pluviated in the lab. So a prepared specimen in the lab because they could not get high quality samples. And then this was one done by the frozen technique, which is, when it's really important, you can spend the extra money to do the frozen technique. And look at the difference in terms of this soil with about the same relative density as the soil that was deposited in the lab. So fabric is the key reason why these two soils with the same confining pressure and the same relative density are so different in their resistance. Don't take advantage. I mean, don't skip the step of just looking at the specimens. For example, after testing, we look and we see that we have relatively flat linear lines showing the layering. So if they were curved significantly, that would tell us that we have a disturbed specimen. You can't actually prove that a specimen is perfectly undisturbed. In fact, no specimen is perfectly undisturbed. You can't even prove that it's nearly undisturbed. What you do try to do is you try to prove it's disturbed. And if you can't prove it's disturbed, then you can say it's probably high quality and it's close to being undisturbed. So by not seeing evidence of disturbance, I go, okay, these might be undisturbed. But then I look at it with different ways. One of the techniques is when I reconsolidate it to its in situ stress, what's the change in void ratio divided by its initial void ratio? The bigger that number is, the more disturbance you're getting and the poorer the quality of the specimen. You can see, for example, the fixed piston shown here in the dotted line or dashed line versus block sampling, which is probably the best sample. You preserve that with a fixed piston. A Shelby tube erases a lot of that, as shown here. Shear wave velocity is another way of indicating whether a soil is disturbed or not. And so we're checking shear wave velocities in the field versus shear wave velocities of our lab specimens, and we're essentially getting pretty good agreement. But again, just because the shear wave velocities agree doesn't mean it's undisturbed. It just, what you're looking for is, do the shear wave velocities differ significantly? That's saying it's disturbed. Because I could have a soil where I shear it and it contracts a little bit so it's denser, but then I break some of the microcementation. Those are two compensating errors. And the shear wave velocity might be the same, but it's actually somewhat disturbed because you've got the contractiveness is causing the void ratio to go down. It's now denser, but I've broken the bonds, which has it's changed the fabric a bit. So again, you're doing these tests to look for disturbance. In the end, look at the results. These are tests on specimens that have moderate densities and also slightly lower densities. These are tip resistances. And the data is consistent. It's following along essentially the same line, whether it's a clean sand or a slightly silty sand. Same thing for the higher density. But then when I look at a clean sand with a low tip resistance, so it's a very loose soil, the results are all over the place. So my own data is telling me, as carefully as I try to sample these with the Dames and Moore, because it's a clean sand and there's no silt in it and it's relatively loose, then I'm getting different amounts of disturbance, which is causing the results to be all over the place. How do you compensate for sample disturbance? Because there'll always be a little bit. If you've got high quality specimens, I favor the Barham recompression technique, where you reapply your best estimate of the in situ effective stresses, which most soils are anisotropically consolidated. So you want to recapture that anisotropic stress state. Professor Ishihara, I've worked with him, and he likes to do cyclic triaxial tests where we won't necessarily have anisotropic loading. And the way he compensates for that is applying a vertical effective stress that's 1.1 times the in situ vertical stress. The idea is to compensate for some of the disturbance to get results that are consistent with what he would have gotten if he had less disturbance. If you have clay materials, there's the classic Shansett method, where you go beyond the preconsolidation pressure and then back it off to get normalized properties. That works well for clays. And then on projects, I've done my very best sometimes to take high quality specimens, and the sample comes up to the ground surface, and in front of my eyes, it essentially it expands, and I see it pushing out of the tube on both ends. That material is going to be almost impossible to sample, and so you can still do reconstituted specimens in the lab. You can look at things like the effects of relative density and effective confining stress, but you need to remember that those samples that you reconstituted in the lab do not have the fabric that represents the fabric in the field if you haven't captured that, and therefore you're missing the quasi-steady state line. You're missing that all-important fabric effect. That's why we often rely on in situ tests. In North American practice, and I think it's happening also in South America as well, is the sonic has become a very popular tool because it's relatively inexpensive and it's fast, and you get nearly continuous logs. In the U.S. practice, in New Zealand and Canada, where I've worked, it's typically a 1.5 meter long plastic tube that retains the soil. I've never had a tube that doesn't move back and forth. So that tells me I'm not getting 100% recovery. By definition, I'm getting some disturbance. And in fact, this is showing me I have soil, but it's not capturing the layering and all that important stuff. And so this is a sonic sample that was taken from a depth of 3.65 meters to 3.9 meters at a site. We've done series of CPTs there, including mini CPTs. Remember, CPT is useful, but the tip resistance is measuring over a zone that's typically, 5 cone diameters. So you're not seeing the layering. That's why I like to do high quality specimen sampling, not just for the laboratory testing, but so I can see the soil. I'll actually take samples of high quality soil samples, bring them in the lab, extrude them, strike them a little bit at the edge, and then split them open so I don't get smearing across the entire specimen, and actually see what the soil looks like. So let's show that in a project I worked on a few years ago. Treasure Island is a site that has liquefiable materials. There was liquefaction that occurred there in 1989. And so if that area is going to be developed, it had to be improved. And so a Japanese contractor had won the preliminary bid to essentially take 4 large H-beams, large metal beams with a big weight and vibrator, and to push it through that material to densify the fill show material, which was the liquefiable material on top of the soft bay mud. And so this is the material that had to be improved in terms of liquefaction, the fill show material. So of course you're going to do test cells, and these are 4 of the test cells. This is the light blue is the ground improvement of CPTs, showing you the very low CPT resistances, less than 5 to 10 across the entire depth, the upper 14 meters. Then after densification occurred, either 17 days to 31 days afterwards, that's what the red and green lines show. This is the improvement. And there's improvement, and then there's not. There's improvement, and then there's a depth where there's not. And so the question is, why is this technique that's going through the entire 14 meters of material densifying satisfactorily the top material, but not the bottom material? Upon further review, the upper material in this area is a hydraulic fill that was built by humans about 60 years ago. The bottom material has the same CPT signature initially, but it's a different material. It's built by nature, and it was once exposed. It was essentially wave action, and animals and little bugs all lived in this material, and so it's a different type of material. I do like looking at tip resistances versus I sub G. You can take a look. This is a work that Peter Robertson has done based on some work that Rob Moss had done, where they recognize that most of the soils that we use and our correlations are built on, kind of the quartz, feldspar sands that are the normal soils that we've dealt with in geotechnical engineering, they should fall between the 100 and 330 kg star line. I see a little difference between the shoal and the hydraulic fill. So let's take soil samples, not just to do laboratory testing, but to see what the soil looks like. The upper fill looks like a clean sand, and it's no wonder it liquefies because it is relatively loose. It's clean sand. The vibratory method densified it and improved it significantly, and so it's going to be resistant to the next earthquake loading. Whereas the shoal deposit, when we actually looked at it, this is an actual soil sample, and this is a blow up of it. It's not a homogeneous material. It's essentially got holes where maybe a worm went through and they got backfilled. At any level, it's not a CH, it's not an SC, it's not a clay sand or hypocystic clay. It's layering and layering and layering at many different scales. And then if we look at it with scanning electron microscope, it's blocks of sand that have clay film. So the clay film allows it to have a low tip resistance, but the blocks of sand are kind of interlocking, and they provide a lot of resistance. The vibratory technique could not liquefy this material because it's not going to liquefy under normal earthquake loading. The same thing was bared out in the laboratory tests. This material is resistant to vibratory or earthquake-induced liquefaction because of the fact that it's got a very different fabric. And you can see that fabric when you look at it with the high-quality sampling. So in closing, we know that soil response depends on the density, stress, but importantly, the fabric, as well as the overconsolidation rate, ratio, the aging, a number of other effects. But I really want to stress the importance of fabric. The CPT is a workhorse, and it can capture many of these effects, but not all. You're not going to be able to see the layering that we just saw at the detail. It wasn't able to discern the difference between the shoal material and the clean sand material. There will be a need to take high quality specimens. And if you're going to do that, you have to work toward minimizing any sample disturbance effects. But realizing that they can never be eliminated, you need to have a way to consider them and address them. The Dames and Moore fixed piston sampler can retrieve high quality samples, vastly superior to anything you can get with a thicker walled, without constant inside diameter Shelby tube. That is an open tube, and it's not a fixed piston sampler. It's important to look at the layering in a tailings dam and also in natural soils. Sometimes it will only allow you to qualitatively change things. But it's important to always see soil the way it is and not just rely on our CPTs and our test results without engineering judgment, without thinking about the geology. Always consider the geology. The depositional environment affects the fabric. Fabric affects the quasi-steady state line, which affects how a soil responds both statically and cyclically in terms of, let's say, liquefaction. And that's why I did this early in my career. And then I became so familiar with soil and the cone and my shear wave velocity tests that I got away from it, to be honest. And now I've gone back and realized, take continuous sampling over the critical layer and look at that soil. Maybe take some additional sampling and then do some high quality testing. But just look at the soil, and it will forever change the way you interpret your results and you consider what's actually happening, because so many of the things that we deal with are system properties. And so it's not the element of soil that matters, it's all the elements together and how they're interacting. It's the flow of water during the liquefaction event that needs to be considered. Thank you.
Thank you, Professor Bray. That was awesome. We really appreciate your time and insights today. It's great to hear you highlight the importance of soils fabric in the field and how field tests are far more representative if you have a high quality data. Just checking the chat here. We move on the questions and answers session. I'll read the question from the chat, but I can see that people are a bit too shy to ask questions in the chat. Yeah, I have one question here, Professor, about the sampling. You said a lot about the DM fixed piston. Here in Brazil, one way of sampling very used is the Denison sampling. It's a well-known method here. Yeah, Denison. It's a well-known method here in Brazil. I would like to hear your thoughts on this method. Is it an effective way to obtain high-quality samples?
Okay, so my view is there's three types of samplers in the world. There are disturbed samplers, like the SPT sampler. You get some soil back. There's a Shelby tube where you just push the soil and you get some soil. You can do index tests with those. Then I have found when you get into looser sands, medium dense sands, silty sands, soft clays, that there's a few high quality samplers out there. The Dames and Moore is one of them. For research, the Laval sampler has been highly successful in some of the quick, sensitive clays in Canada, and they've also used some of these high quality sampling devices in Norway for some of the quick clays. So those are really at a whole nother level for those cases where you have those. If you can, the Dames and Moore is going to get a better sample of those kinds of materials. Now, it comes a point where the Dames and Moore will not be able to shoot the entire 45 centimeters. The soil's too strong. The tube will not be able to extend the full amount. And so then I've moved toward a pitcher barrel or a Denison. Where I have practiced, the pitcher barrel has been more available. So, you don't just go by the best sampler, you go by the best sampler that can be operated well by the people who work in that area. And so Pitcher was a drilling company that worked in the San Francisco Bay Area. So they really dominated the West Coast of the United States. And I'm more familiar with the pitcher barrel. And it's similar to the Denison. And I think the quality of the specimens, if done right, would be similar to that. Both the pitcher barrel and the Denison are going to be fine for stiffer, stronger soils. They're not going to be able to get high quality specimens of some of the looser sands and some of the highly sensitive clays.
Okay, very good. Yeah, and then that's always a way to evaluate the quality of the sample. Yeah, that's very good.
No, and another thing too is they didn't have a Dames and Moore hydraulic piston sampler until Turkey until I went there and I showed them how effective it was. Now they have a Dames and Moore hydraulic piston sampler in Turkey. Same thing in New Zealand. I went to New Zealand in 2011 and they did not use the Dames and Moore piston sampler, but now they do. And they know when they have difficult materials, when they have some silty materials, some looser materials, some clay materials, and they want high quality specimens to do high quality testing, they now have the Dames and Moore hydraulic piston sampler. And so I think that if companies run into soils that are, soft, very soft to medium stiff clays, or they run into sands like I've been testing that are silty sands that can liquefy. Uh, if you ask for it, a company will get that device. It's relatively straightforward to use, and you'll get better quality specimens for those soils. And then when you can't shoot that tube, then you use the Denison.
Awesome. Yeah, that's a good opportunity for us here in Brazil to start using this kind of sampling. Yep. Just one more question, Professor. I can see that here in the chat. We don't have any question at all, but yeah, just to finish here, at the beginning of the presentation, you mentioned the Idris and Boulanger methodology to evaluate the factor of safety against the liquefaction using CPT data. Although CVD testing is widely used in Brazil, SPT test remains the most common here. So the question is, could the Idris and Boulanger methodology also be applied to using SPT data? I mean, for preliminary analysis before conducting further tests? And what would be considerations or concerns regarding the application of this methodology with SPT data comparing to CPT data?
Yeah, one is Boulanger and Idris. There's Idris and Boulanger 2008, and then they have an updated relationship, Boulanger and Idris 2014. They have focused on the CPT, but they also have the SPT procedure.
Yes.
And there are other procedures out there that do SPT. SPT, unfortunately, we've done all these things to standardize it, but it's still not standardized. People do it slightly different. And for example, you should have a constant inside diameter. Some people like to have the little rings inside of it so they can actually look at the soil in pieces. That can change things dramatically, whether the rings are in there or the rings are not. So there's so many things that can be done wrong. If you're going to do the SPT, you have to follow ASTM 1586 and 6066 line by line. But even if you do that, you have to measure the energy. That's good agencies, people working on dams, people working on high profile projects. The regulators and reviewers in most countries have realized the big uncertainty there is if you don't know what the energy is. And so you have to measure the energy. And measuring the energy on the rig one time 3 months ago, when there was a different weather, a different operator, the machine had so much grease on it, and then saying, oh, I can just use that same value on my project, that's a very dangerous thing to do, because I have found rigs where they swore it. I measured the energy 3 months ago and it's 82.3%. And then I measured on my project and it's actually 90% or it's 66%. You're taking that blow count that you measure and you're multiplying it by that energy ratio, and you can be off by 50%, you can be off by 100% if you don't know what the energy is. And so you can use an SPT based procedure, but you've got to follow the guidelines and you have to measure the energy. Otherwise, I think there's just so much uncertainty. I'm working on a project right now in a country that has no access to the CPT. There's no CPT trucks in the country. So they're doing the SPT. And I go, how do you know what the energy is? And so they took my recommendation to actually get the energy out there, and they're measuring the energy, and they're finding out what they thought the energy was wrong. So use the CPT. It's standardized. It's nearly continuous. It's clearly the preferred method. But if you don't have access to the CPT and you have to use the SPT, then you have to measure the energy.
Good, Professor. Yeah.
You're going to potentially make $1 million decisions based on whether the blow count is 15 or 25. Yes. Yeah. And the number can be 15 or 25 for the same soil, depending on the energy. Like I said, I've measured energy as low as 30% when they told me it was 60%, and I've measured energies above 100%. All of these are rigs that say, oh, I know what the energy is, trust me. I don't trust anybody with soil mechanics.
Totally agree, yeah. That's for a preliminary analysis, it's okay, but it's better to conduct further tests.
I think even for preliminary analysis, you just realize you may get a blow count that says the blow count is 15 in preliminary analysis. Then you find out it's actually 7, which makes a big difference. Or you find out it's actually 30. And the difference, so you did all this preliminary assessment with 15, but when you really actually do it carefully, you find out it's half of that or double that. I'd rather do good preliminary analysis with a better tool, which would be the CPT.
That's cool. That's cool, Professor. That's it. Yeah, I think that thank you all, people here that joined us today. I hope you guys found the presentation as valuable as I did. Once again, I would like to say big thanks to Professor Bray, and thanks to everyone watching. We look forward to seeing you in the future. And guys, have a great night. And Professor, you want to give some last words?
No, I really appreciate the opportunity. I have been very forceful in talking about sampling because I think it's so important. Is our profession is only going to be as good as the data that we produce. And I think that in US practice and around the world, we've sometimes just said, well, we can't do this, we can't do that. And we suffer because of that. And I think our client suffers because we're not giving them the most value. I think it's better to do fewer samples well and make some good, have a good basis for making your engineering decisions. And I've been on projects where someone wants to hire me to do advanced analysis. And I go, let me have the data. And the data is very poor. I said, you know what? Instead of hiring me, you should spend the amount of money you're going to spend on me and do better testing, because better testing done without me will get you better results than me.
Yeah.
I can't do anything if I have no basis to calibrate my numerical model.
Yeah, it's better you spend your money now than spend 10 times more at the end.
Yes. Yes.
Yeah. Okay, Professor, have a good night,
Okay.
everyone. Good night.
Yeah. Thank you for the opportunity of speaking with you today.
Thank you.